in some science education for your kids and for yourself. I'd like to acknowledge that we are on the lands of the of Sanic people, and they call this hill Wetixis, and it is on unceded territory of the First Nations here. Very happy and honored to be able to work and here on. It's really nice. I'd like to introduce David Payne to you today. David has not been in Victoria for very long. When did you decide that this was going to be God's country and you were going to come out here instead of being in like Alberta? You know. About a year and a half. Okay, about a year and a half. He did fine. He really well when he came out here, and when he came, he lives kind of up island a little bit, and he says, "Oh, I think I'm just going to come in and come into the Royal Astronomy group and see what's happening there." And we found out very quickly that he is one of the most incredible astrophotographers that we have in Victoria. And we didn't know that beforehand. And it took a little bit for us to find out, but he would just kind of go, "Well, I've got a picture. Would you like to see a picture?" And we went, "Oh." and ever since, he hasn't been able to get away without doing some any astrophotography for us. On other nights, he comes up to the hill and he'll bring up telescopes and he'll tell you all kinds of things. But so tonight he's going to give you a little bit of a presentation on some of the work that he is doing with the Royal Astronomical Society and helping out the Friends of the DAO. Thank you, David, and also a little bit about the star party that's going to be in August. There's going to be another, and he'll tell you a little bit about that a little bit later. Okay, so I'm going to send it back over to David, and I'd like to have you give him a warm welcome. Thank you.
Thank you, Laurie. As Laurie said, I'm David Payne. I am not a professional astronomer. I am an amateur astronomer. So what I'm going to do is, what I like to do as a hobby is take my telescopes in my backyard and take pictures and trying to figure out what's going on out there. So rather than just show you a bunch of pictures, what I've done is made the pictures tell a story of what is actually going on. And I couldn't cover everything, so I thought I'd start tonight with what I'm calling part one, where there'll be a part two, depends on part one. But I want you, by the end of the little talk, I want you to be able to look at a galaxy, and when someone shows you a picture of a galaxy or you see one on a TV show, a nova or something, you say, "Oh, I know what's going on there." So you can tell me at the end whether I succeeded or not. So while I am not an astronomer, I am a scientist. So I do come with a bit of a toolbox full of things I've learned. I'm actually a chemical engineer. I'm retired chemical engineer. But a lot of things, the chemistry, the math, the flow of fluids, as you'll see in a second, and other stuff. It's what my career was in. So that helps me interpret what I read. What I did in the early part of my career was actually look at flow of different fluids underneath the ground. I was actually in the energy business, and I know that's not the greatest thing for this part of the world, but there's a lot of analogies. We would use sound to actually look into the Earth. So that was our telescope. We had probes or little tools we would send down wells to measure rock properties and stuff like that. And we would gather all this static data. We'd have a geologist who would try and interpret what's going on. We put it into a big simulation model, just like the simulation models they use in astronomy. And we put all of our time-related data in there, and we try to make predictions as to what's going on and what's going to happen next. So there's a lot of analogs. This isn't the first universe that I've explored with a camera. A few years back, I was a diver, and I've got all kinds of pictures taken underwater, trying to figure out what was going on there. So that's my background that I'm bringing this to you. Now, if this is one of the earliest pictures I took, it's of a star-forming region in Orion. And this is a famous Horsehead galaxy up there. I'm going to use the mouse so I can point to it. Now, when I was a kid in the 60s, my dad bought me the Rand McNally 1964 Atlas of Space Atlas, and I still actually have it right here. It's worth a look because it's worth a look afterwards because it's got some of my hand scribblings as what's my favorite planet, you know, and I sort of ranked the planets, and I like this one. But that picture in the upper right was taken, it's in this atlas, and it was taken of an example of what a nebula was. And it was black and white, grainy, and I found today with a digital camera and a telescope, I can take pictures that are better than that, and I can take them in color. So that's how far technology's changed since, maybe I'm just getting old. Here are my fleet of telescopes. Now, if you get into astrophotography, you have to kind of get into it big time before you want to buy all this. But the far one is take magnificent pictures with it. It's my little portable scope. But don't buy it all at once. Buy a little bit and then see if you like it if you take it up as a hobby. Pardon me?
She has a question there.
Sure.
What's a nebula?
I'll tell you exactly what a nebula is. Okay? The focus of today's talk will be on galaxies. And this is a picture of a galaxy. I hope everyone can see it just right. Taken by a friend, also RASC, Brock Johnson. I don't know if he's in the audience right now, but this is his picture of a galaxy that's given the glamorous name M101. There's a bunch of things that are going on here. One thing is you can see it's got a spiral shape to it. So I'm going to tell you why it has a spiral shape. There's some other things that are going on. You can see this sort of cloudy mist around the edge. Well, we're going to show you in a second that those are actually stars. And you can also see when you go into the middle, this is very far away. This is like 27 million light years away. When you get into the center there, you see it goes orange, changes color from this blue color on the outside, blobby color. And then the other thing you might pick up on in the middle there is there's some red little lines. That, well, bored hydrogen. It's really called a molecular cloud. It's got mainly hydrogen in it. It's got a few other elements in it, kind of is like spice. And it kind of is either a dull red color, browny red, or even a dark and sometimes a gray, depending on the light that's reflecting off it. And it's kind of in the spiral too. There's a few things going on the outside. When you see something that looks like a star, it generally is a star, but everything that you would identify as a star in this picture is actually a star in the Milky Way, because we have to look through the rest of the Milky Way when we see the galaxy. There are a few things that aren't, and I will get to them in a second. Oh, the other thing I want to note with this picture is that it looks like it's been in a little bit of a fender bender. There's a bend right here and a couple of extra wheels. It's not a perfect spiral by any stretch. Now, if you look this up, you say, okay, well, what is this composed of? Well, often you'll get the names of things that are kind of arbitrary and kind of point to what it is so you can communicate that you're talking about the same thing. It doesn't really tell you much. This is my version of the same galaxy. I've made those dark molecular clouds, those bored hydrogen, I'll call it, molecular clouds, a little darker. But I've also used a special filter here that makes excited hydrogen glow this bright red. So the four things you can see in the galaxy now are the bored hydrogen sort of circling in the middle, the bright red excited hydrogen, the red, you can see blue blobs on the outside, and it goes to yellow in the middle. On the outside, there's a couple of things I would want to point out. Over here, this is actually another galaxy. This is a satellite galaxy to this galaxy. And this actually the thing that causes these arms to bend, because there's gravity pulling each other. So while this galaxy tries to be nice and spirally, there's these things that are kind of mixing it up. There's another little galaxy. This one's entirely blue. The other thing I'd like to point out is over on this edge, hopefully you can see over on this edge, there are two stars. Like I said, these are Milky Way stars because we can actually see them as stars. This one's blue colored, and this one's kind of orangey red colored. Just like this galaxy is orangey red in the middle and kind of blue on the outside. So there's a secret to interpreting this. And here's all the things that I hope to talk about by the end of this presentation. So I pointed them all out to you. So this is the first chart. I'm not going to show too many of these charts, technical charts, but I want you to look at the one on the left-hand side. And basically what we've plotted is the color of a star versus the brightness of the star. Now this is on a very wide scale. Our sun is kind of a yellow. It's defined as 1 because this is how many times brighter or dimmer than the sun the star is. Over here at the 1, it's a yellowy star. If you see the star is blue, it's up here. Let's say it's here. In order, these blue stars will be 100 times brighter than the sun. If it's a red star, it's down here, it might be 1/100th as bright as the sun. So how does these stars get so bright? So the color of a star tells you a lot more than just how bright it is. The second thing it tells you, and it's by way of, in order to shine brightly, a blue star has to burn a lot of fuel. So it has to burn a lot of hydrogen. So like a blue star, I think, lasts anywhere from 10 million to 100 million years. That's quite a long time. But a star like our sun is going to last 10 billion years. So anywhere from 100 times to 1,000 times longer than these bright blue stars. So they have here I am, a huge, massive, bright star. Yeah, but you're not going to live that long at that rate, right? Like,
Did you calculate that in quasars?
In
Quasars.
quasars, you might be able to.
No,
No. No, quasars are a totally different type of stars. These are main run-of-the-mill stars. So I can skip this. So this star in this corner is going to last a lot longer than this star. You might not see that brightness difference because we don't really know how far these stars are. But from the color and the brightness, you can pretty much guesstimate how far away the star is. Now I'm going to convince you that in this galaxy, the blue around the edge, the bluer and the clumps you see are actually blue stars burning really, really bright. They haven't been there for very long, though. They only live 100 million years. In the center of the galaxy, it's yellow or can be reddish. those are long-lived stars. Okay, so you got new stars around the outside, blue, and old stars in the middle. The second thing I will note is that I told you the difference between excited hydrogen being bright red in this picture and sort of bored, just nitrogen, cold nitrogen, or bored nitrogen or whatever. It's kind of more in the middle. Well, all of these stars that we're looking at are actually made out of that cold hydrogen stuff. So that's what it makes. That's what the star burns. And when it's excited, when a star is actually made, it gives off a lot of UV radiation, which excites the hydrogen and makes it that bright red. So the bright red areas are telling us, hey, they're like a flashing red flag saying, there's some new stars being created here. And where it's not really red, it's not really doing much. I'll show you more on that in a second. So that was a spiral, looked face on to the spiral. We can also see this one, I think this one might be my picture. This one, we're looking at it edge on. So you can imagine the spiral going up like this, and all that cold hydrogen it's quite transparent, but not transparent over large distances. And you can see it actually almost blocks out the center of the galaxy. In this particular galaxy, you see a few sort of red spots, particularly on this lower arm, and it is a little bluer on the edge than it is in the middle. But you can contrast that to this next galaxy, which is almost all blue. So it's almost made out of completely new stars. And there's quite a few more red blobs along it. But there is also some cold hydrogen, and it's starting to block out the center too. So rather look at edge on and face on, here's one that we can look at an angle. This is the Andromeda galaxy. So it's only a couple of million light years away. So it's actually the closest big galaxy to our own. So it's following that pattern. You can see that cold hydrogen is really thick and sort of chunky around the edges, but by the time it spirals in, it gets thinner and thinner as it gets towards the middle. You can also see around the edges some new blue stars. So I took the big telescope out and I wanted to show you that these are indeed stars. So I'm just going to zoom in with another telescope on the left-hand side, although left will become right in this. So this is zooming in to our closest neighbor. So if you look at all these, what looked like a blue mist when you were zoomed out, now you can actually see little tiny stars. So these are stars that are actually in a galaxy. And you can see that cold sort of bored hydrogen is all around the edges where all these new stars are. Whereas if you go towards the center of the galaxy, you can see that the image turns a yellow color. So when we're going towards the center, I actually lose resolution of the stars. There's more stars there, and they're also a bit smaller, so we can't really see them. So I'm going to cheat and use a Hubble telescope version. So it shows you essentially the same thing. The red isn't highlighted in this image, so you can't really see the excited hydrogen that much. But you can see it's almost like I don't know if you've ever seen a pointillism painting where they just make the whole thing out of dots. It's got that kind of effect to it. But you can see these are actually individual stars going from those old stars in the middle towards brand new stars, relatively brand new, if you can call 100 million years brand new, stars towards the outside. So I think I explained this enough. There are some exceptions off this main trend, but we're not going to worry about that right now. There are a couple of, in my image, there are a couple of reddish spots. I haven't actually highlighted. This came through naturally. There's one there. There's one up there. You can see they actually have some blue stars in the middle of them. And you'll see why in a few minutes. This is a picture that another friend at RASC, John McDonald, took. And this is of our Milky Way. And it's just taken through a normal camera. It was on a little bit of a mount that turned so that you could keep up with the galaxy. But you can see that same sort of stippled effect and stars that are in this galaxy as you could see in Andromeda, which should be reassuring because it would be really weird if Andromeda was made out of something completely different than our own galaxy. So, but what it does allow us to, if I want to look at the bored hydrogen, I don't have to look into another galaxy to figure out how it works. I can look in our own galaxy. It's a lot closer. Here's some excited hydrogen going on. And I can look at what's going on in there and figure it out by looking at our own galaxy. And that way I know what's going on in the far galaxy. Someone's actually, with a combination of actual measurements and imagination, have come up with their own spiral map. So some imagination in this, because we're looking at edge on, so we have to make some things up or guess, educated guesses. If you looked at our galaxy edge on, the only thing I want to point out here is it's a little bit bent too. It's not perfect either. And I meant to point out with the Andromeda galaxy that it looks like it was in a little bit of a fender bender too. And it had, that's what I wanted to point out. Never mind. It had a couple of little companion galaxies just off to the edge too. So M101 has had them. Andromeda's had them, and we've got them too. They're called the Magellanic Clouds, large and the small Magellanic Clouds. We can't just see them from the northern hemisphere. You have to be in south of the equator to see them. But they're there. And the other little bit of a difference is the middle of our galaxy has a bit of a bar instead of just a circular center. Just for information, here's our sun right here. So we're kind of midway out on the ride of this thing. So here's another image, and this is of a cluster of galaxies. This is in Virgo, in the constellation of Virgo. And all I want to point out here, there is some spiral galaxies that you can see in the distance, like here, there, and there. And there's also another kind of galaxy in this one. And it's called an elliptical. And there's two up there in the middle, and they're kind of fuzzy blobs. They don't have a lot of structure. They don't have a lot of character. There's another one right down here. They're kind of boring. And when you look at it, they don't have any hydrogen at all. In fact, this is an image I've actually tried to highlight any excited hydrogen, and I didn't find any in those elliptical sort of things. I didn't find any actually in the spiral, much in the spiral galaxy, a little bit here and there, but very little. It's mostly cold hydrogen. I think that's it for this slide. So we've got three kinds of galaxies you've seen so far. One is irregular, and if you recall that one off of M101, I'll show you it again in a second. It's kind of just a mess. It's got some excited hydrogen, usually has a lot of excited hydrogen, a lot of new stars, nothing really old. Then there's the spiral galaxies like M101 and our own. And then there's these elliptical sort of fuzzy balls, I guess. Unfortunately, this one colors it's blue. They won't be blue. They're all orangey. Well, what does that tell us? All these things are made up of old stars. There's no new stars in them. So this is the classification of galaxies, and I'm only showing you this because galaxies tend to be irregular when they're first formed, and they go through spiral phase, and then when they're very old, they become elliptical and eventually round. So I just want to tell you why that is. But before I go, I just want to show you in the upper left, that's that satellite galaxy to M101, and it's that irregular galaxy. It's just a mass of new stars and excited hydrogen. Here's another galaxy. It's got a little bit, it's mainly round with blue new stars, but it's got a little bit of hydrogen off to the edge of it. So it's really irregular. But essentially, the hydrogen is lit up here, is part of this arm here, and we also have the cold hydrogen, the bored hydrogen, highlighted in that corner. So what's going on with the spiral galaxy? Well, I'm sure, especially the young people, when you do the dishes, if you don't do the dishes, go home and do the dishes for the next few days, and you can try and do this experiment in the sink, or if you're reluctant to take a bath, and you can do that too. But what you'll see is when you pull the plug on a sink full of water, you'll see it start to spiral round and round. And that's the Coriolis effect. It goes by lots of other names. There's a separator, what's it called? A vortex separator. So it creates a little vortex. And if you were to plunk some dye or food coloring off to the side, you can see initially it's not affected by the drain, and it's forming clumpy sort of objects. It hasn't fully dispersed yet, and it's not really feeling the effect of this vortex. Well, that clumpiness, take that as an analog to that cold hydrogen, those big clouds that were on the outside of the galaxy. And as the gravity of the center of the galaxy takes effect, it'll start to spiral inwards. And you can see just before it goes down the drain, right about there, it's using my microphone as a pointer. It becomes very fine just about as it goes down to the drain. Well, that's going to be important because the whole spiral pattern of these galaxies happens because that gas is a continuous sort of fluid. If you threw a bunch of marbles in here or floating things, you'd see them bump into each other, and they really wouldn't form this nice spiral pattern. So in order for the spiral pattern to occur, it has to be a proper fluid. It can't be a bunch of stars. And so the whole driver for the spiral pattern in M101, the whole thing that causes it to be a spiral, is actually this cold hydrogen spiraling down into a black hole in the center of the galaxy. Out here where it's clumpy, it can form new stars. And those stars form where the hydrogen is. So the stars actually form that spiral pattern, not because they're going to do a spiral pattern, because that's where they were placed. That's where they were born. And when we get to those old elliptical galaxies with no young stars, with no hydrogen, well, the stars are free to go in whatever direction they happen to want to go in. And you won't get a spiral pattern. Get something more like an egg timer is a good example, or there's various sort of examples. Each one of the grains of sand it's not bothered about leaving its neighbor or anything like that. So you won't get those same spiral patterns with an egg timer and just stars. So it's that hydrogen cloud, those molecular clouds that are actually forming the spiral. Going back to our old Virgo cluster, you can see when I zoom in to a lot of these spiral galaxies, you can see the hydrogen in them creating the spiral. Right? You can see those cold clouds. When I get to those big old ellipticals, there is no spiral pattern because there's no hydrogen in them. The stars sort of just mill around a central point. There is one example of non-regular, or what do they call it, a regular galaxy, and that's because it's being influenced by its satellite. And you see that that'll be important in just a second. How am I doing for time here? I gotta speed it up. So while I was sometimes when you're exploring, you get sort of pushed off to the side. You get was it the squirrel? What is that? You get. So I was trying to study this. This elliptical galaxy over there, when this guy came out of nowhere and started photobombing my camera images. That turned out to be a meteor. So I could look out and find out that's what it happened to be. And I found out some information and I calculated some other information on it. But sometimes serendipity hits when you're in the middle of a study. So here are two galaxies. The one on the right essentially looks like there's not much blue in it, so it's mainly old stars. It does have quite a bit of hydrogen in it, but you can see its arms, its spiraling is quite tight, quite regular, and the spirals are very well defined. And it goes around that galaxy maybe 1.5 times each of the arms I tried to count. Look at this galaxy over here, though. It's kind of broken out. It's been in a bit of an accident. Now, actually, there's another galaxy that's off this picture, and the gravity from these other two galaxies kind of stirred the pot. So it might have been nicely behaved like that at one time, but someone's come in here and sort of messed it all up. And what that does is it makes the hydrogen clumpy, like it was away from the center before. And then that clumpy hydrogen is what makes the stars. You can see these nice blue stars forming in it, and you can see lots of excited hydrogen saying, hey, I'm making new stars here. So, and one of the things, it might not be just a neighboring galaxy, a little dwarf galaxy off to the side. Over on the left-hand side here, you'll see this is two galaxies actually colliding and merging. So nothing's going to mess up that spiral pattern quite like that happening. So when that happens, you can see those galaxies. I actually don't see any. There's a little bit of excited hydrogen in there, but they're really blue. Like there's a lot of new stars being created while those galaxies merge. And here are a couple of galaxies that are just generating stars like all get out. And you can see they're kind of misshapen, right? So they've been in a bit of an encounter with another galaxy. This one's called the hockey stick, and this one's called the whale because it looks like a whale in profile. And I think this little offshoot galaxy might have something to do with this one being disturbed. Here's another galaxy. This is the Triangulum galaxy. I think Star Trek visited it. This is without the red enhancement. Even without the red enhancement, you can still see a lot of excited hydrogen, All the stars seem to be blue except maybe in the very center. And this other picture over here is just a picture of the excited hydrogen. When you put it together, you get all sorts of excited hydrogen all over the place saying, hey, I'm making stars here. Some of them are forming loops. You see the one at the top and the one over there. Really nice patterns. Here's another galaxy. This is Bode's galaxy in the north. On this side, we have a nice behaved galaxy. It's got some new stars on the outside. Everything's nice. And then you got this galaxy over there. It's called the Cigar Galaxy to its shape. And this is an image by Ken McGill, another RAS person. But you can see there's this picture hasn't been enhanced to show the excited hydrogen. But you can see the hydrogen that it is, it's no longer even in a spiral pattern. It's kind of all over the place. When I show a picture of that same galaxy with the excited hydrogen shown, you see it doesn't even lie in the galactic plane. Lots of blue stars, but there are stars being created all over the place. So this will continue, and this galaxy happens to make a sun-like star every single day. So that's how many stars are being created. So it's just super active. Another example of a lot of blue in that central galaxy there. And when I zoom in to look at the excited hydrogen, you can see there's some additional arms that are just made out of excited hydrogen. So putting that all together, and yet another galaxy. This one doesn't even have a very good spiral shape. It's got sort of a spiral shape. This is called the Sunflower Galaxy. But you can see all that excited hydrogen in there, meaning there's a lot of stars being created. So I'm going to quickly look at that hydrogen, those molecular clouds in our own galaxy to show you what's going on. This cloud is actually just outside of our galaxy, adjusting out the plane of the galaxy, and it's reflecting back the glow of the galaxy itself. So it's a general gray color. Here's another molecular cloud. You can see how it's kind of cloudy in the background. And these are some stars that happen to be passing through. They're not associated with the cloud. They just happen to be passing through the cloud, which kind of goes to my point that the stars are doing what they want to do. They're not necessarily going in the spiral pattern. But as it goes through the cloud, the light it shines, these are new stars, makes this nice blue pattern. This is the Pleiades, or Subaru as it's known in Japan. It's a beautiful star formation that you can see with your naked eye in late fall and winter. Here's another pattern that shows stars moving through a cloud. You can see those clouds can get very dark in places. And I don't know if the whole pattern of this, but it looks like helping hands. It's called the helping hands nebula. And get to your question about what is a nebula. A nebula is just some of this molecular cloud that you can see for various reasons. Either light's being reflected off it, it's like the excited hydrogen that's giving off light of its own, or it's stuff like that. But it starts blowing it away too. You can see this is called the stellar nursery. This is called the Fly Nebula. And you can see those stars right in the middle of that blue area. Those are new protostars that just turned into stars, and they're lighting up and exciting all the hydrogen that's around it that created it. And now it's creating solar winds, which are that UV radiation plus some other ions. Is giving off all kinds of stuff and is blowing the clouds away. The very clouds that formed it. Here we can see some bubbles forming. This is the Tulip Nebula because it looks kind of like a tulip, but you can see some new stars in there. They're actually forming bubbles inside as they are creating. And that leads me back to my original diagram. Original figure. There's some stars being created in here. There's some stars being created behind that horse head. And if you look kind of closely, you can see these striations coming up from that yellow bank. Those are those jets of stars still being created behind that horse head dark nodule. So we know there's stars being created in here. Well, the hydrogen's telling us, hey, I'm getting UV radiation all over the place, so I'm creating some stars. This is one of Brock's images. You can see what we were just looking at is just down here. It's part of a huge molecular cloud. Up in there is the Great Orion Nebula. This star here is actually the Orion's Belt, the furthest left star in Orion's Belt. But it's just a huge molecular star. And you can imagine what this looks like if someone on another galaxy was looking at us with a telescope and seeing what's going on. You can see lots of formations. This is further on in the life. This is the Elephant Trunks Nebula. There's clusters of stars being formed, and you can see it blowing away the hydrogen around it. This hydrogen will eventually get blown away and drift off and actually form new stars. But you see, it doesn't completely blow away the hydrogen. There's still some really dark nodules that are left over. Those are thick clouds, so it's highly viscous and dense. And so these solar winds, it takes them some while. They get eroded a little bit, but inside, they're not seeing any light. The light's all blocked out. So they're still cold inside. So there's still stars being created in this overall thing. If you come back a few million years and take another picture, you might see some additional stars and start seeing that blow away the cloud from within. Here's one's further along. You can see in the center, there's a cluster of stars. So all those stars are being created. We can also start to see a loop sort of formation happening. And just as a quick aside, if you look at these, here's a couple of nodules that are being lit up on the edge by all that UV radiation, but they're not getting blown away. There's still stars being created in them. And you see those little nodules of dense gas not getting blown away. You see them in a lot of these pictures. And I've got just through some examples of things getting wind blown, because that's what the stellar winds are doing. They're kind of wind blowing these nodules. And you can kind of see the same shape to them, either in trees or in rocks that have been wind eroded or sand blasted. You can sort of see the same sort of shapes in those things. This is a nebula called the Cygnus Wall, and it's just another example. If you can imagine the solar winds coming from behind that dark cloud in the upper right-hand corner towards this way, you can see it's blowing all that hydrogen back. And in here, it's actually quite dense, and there's probably some side where new stars are being created. And here's some of those outlier things, some small ones. They'll probably have stars being created in there too. Here's another one of Brock's pictures. This is of the Eagle Nebula. And I'm just pointing this out because in the center of this nebula, there's some of those things too. Now, just sort of formulate the shape of that thing in your head. And a picture you may have seen before, this time a very famous picture by the Hubble telescope of those exact same area. And these are those nodules being blown from the top down, but they're thick and they're dark inside, so more stars can be created. You can see around the top edge, there's those flares, those are Herbig Haro things coming off. So you know there's stars being created in there. And the guys who operate this telescope called this the pillars of creation, because that's what's going on here. Stars are being created. Of course, thanks to JWST, we have an even more modern, more detailed picture of the same thing. So just a couple of pictures. This is one by Ron Fisher, another fellow RASCal. And it's really prototypical in terms of you got this star cluster that was just created and this loop being formed as the gases are getting blown away. And here's another one. This one's my picture, but this is called the Heart and Soul Nebula. But you can see how these loop formations are happening with the stars creating these excited hydrogen loops around it. And here's another one with the stars removed. This is the Lagoon Nebula. The colors are a little different, but it's essentially showing the same thing. So I go back to the Triangulum galaxy. When we look at this, we can see some of these loops in the corners showing where the stars are being created. So this is in another galaxy. So this is a different galaxy, but we're seeing the exact same thing happening there. Now, one thing I do want to talk about back to this swirling thing. So now we understand why the galaxies are in the swirl. Look what's happening right at the drain. So it's kind of neat the water's sort of bending in a conical form down towards the drain. And what that's doing is when you look at the drain, it's bending the light. It's apparently bending the light around it. So one additional analog when you're doing this, kids, when you're doing this, when you're doing the dishes at home, take a look at the drain and see if you can see how the light's bent around it. Well, back to this galaxy cluster. One interesting thing I wanted to point out is this galaxy behind here was actually the target where our first photograph of a black hole came from. So that was this, it was this kind of run-of-the-mill elliptical galaxy with nothing much happening. It's not very exciting. Don't take too many pictures of them. And here's the black hole that's in the center of it. So it's, what does it look like? It looks like a drain. That's what it is. It's basically a gravity drain. Nothing much else to say about it, but that light you see around it is the light that's bent. This black hole happens to do it in one extra dimension than your drain. Now, all this hydrogen eventually gets used up. It's eventually going to get used up in the universe, either creating stars or getting dispersed where it can't do much, or being sucked into those black holes. So I don't mean to get all Stephen Hawking on you, but don't worry about it. There's still a lot of hydrogen out there. I'm done. So back to our M101. You should be able to look at this now and see exactly what's going on. Well, I'm telling a bit of a lie because this isn't the picture I showed you at the beginning. It's a little different. Oops. Page down. So can you spot the difference between those two pictures? Do you see the little blue? So that is star that's in this galaxy. That's actually a star going supernova. So there's so many new stars being created in this gigantic galaxy that you can actually, they don't live very long, as we talked about, only 100 years or so. So every decade, about every decade, this galaxy gives us a supernova. And that's really at the opposite end of the spectrum and where my talk ends, because that's really about the death of a star. So to finish off, if you're interested in what you're seeing and you want to take a look with your own eyeball, please come to the Island Star Party that'll be taking place in the evening and into the night. We'll have speakers and we'll have viewing through telescopes and all sorts of good things happening. It's happening in Bright Angel Park, which is near Duncan on the other side of the Malahat. And other than that, if you like to look at the pictures, please visit the Victoria RASC picture website, where you can browse these pictures and take a view of what's going on for yourself. And other than that, I can entertain any quick questions briefly. I think I'm over time, so yes, I'm into the next session. But that would be great.
I'm just saying, it's just about 9 o'clock, and people have not been to the dome tour. I just want to make sure that people can get to the
Yes.
like get to the dome tour and not been to a dome tour yet. So I don't think David would mind if you are going to the dome tour to kind of just speak out.
Yeah, just
and
right.
you that want to keep sorry, David, I kind of interrupted you, but I just want to make sure people get to it.
She said it makes her come.
Right.
No, I practiced it.
Yeah.
Too detailed.
Oh, okay.
Around, if you like,
So were there
Oh,
any questions?
you have a question? Yeah, go ahead.
So how does sorry, no, it's okay. Sorry. How do we get like a picture of the Milky Way galaxy if we're in it?
You're in it, but you're looking at the edge.
Oh,
So you're looking at the edge. So when it's summertime and you see the Milky Way, you're looking towards the center. When it's wintertime and you see the Milky Way, you're looking out towards the outer edge. When it's spring and you don't really see it at all, you're looking out.
Yeah. Anyone else have a question? Did you have a
How do you
question?
name stars or galaxies? Like just
naming
just yeah, naming. How do you?
Yeah. Astronomy's been around a long time. So every so often, someone names all the stars and says, okay, now this is a system that's going to last and stand the thing. And then with better telescopes and things, we can see deeper, we can see more stars. So someone else comes along with a new naming system. So a lot of these things have multiple names, multiple categories. And generally what you see is there's catalogs. So it's like going to a shop and you'll see the same item in different catalogs. So stars end up having multiple names depending on what catalog they're in.
There's a hand up over here. Yeah.
Yeah.
Go ahead.
All right, so imagine we're 500 years in the future and you're in a spaceship that's beyond the solar system. What would you be able to see with in the naked eye? Would you be able to see something similar to the night sky or a lot more?
Okay, so it's a very good but loaded question because I get that with my pictures. Is that what it really looks like? Well, if you go out and look at a telescope, well, first of all, it's not what it looks like to me because it's all of a sudden got very blurry. Okay, but and I don't mean that facetiously. It looks different to different people. Different creatures have different things in their eyes, and that's what we're doing with our filters and cameras. It doesn't really look like that to anybody. If you look through a telescope at some of these things, you'll tend to see it in black and white. You don't get much color. And it's because the color receptors in your eye are not very sensitive to dim light. So you in dim light, you see black and white, so everything looks kind of black and white. With the camera, you can keep it on the target for quite a bit of time and you get the colors.
Any other questions? Yep. Here you go.
So the stars are formed by material collecting over a long time in a cold environment, yeah? And yet I'm just intellectually curious how that fits with the theory that the universe is expanding.
Yeah.
Try that one on for size.
I'm just trying to think of the best way to answer that. So the universe is expanding in terms of the space between everything. But that's not really affecting these molecular clouds, they're big, but they're not intergalactic big. And yes, indeed, because of random walk effects, if you put a cloud, it won't collect. It'll just disperse. You think smoke would just eventually disperses, and that's because it's fairly high temperature. All the little particles are jiggling around quite a bit. It doesn't come together. And that's why the cold is required, so that jiggling isn't taking place and gravity can have an influence and other intermolecular forces can bring those particles together. Does that answer your question?
It does, but it also tells me how the universe is also, and I know that's not always been the case.
Yeah, that is really leading edge stuff. In fact, there's a good article in Astronomy magazine about how that might be an illusion. Popular mechanics? Yeah. Okay.
Yeah, I just have online every day. And what do you think of this? And you didn't have time to talk about it.
Okay, another question?
Another question?
Okay.
I get another talk.
Oh, yeah, Stu, and once other people.
Okay, so does law of conservation of matter apply when something goes to a black hole? Does it become nothing, or?
That's another really good but really loaded question. So there's the classical thought that cosmologists tend to apply. That says a black hole is a singularity, a mathematical singularity. And I can't accept that. But I'm not alone in not accepting that. Quantum physicists don't accept that. They're sort of saying, hey, you're talking about something that's pretty small here. You're getting into our universe. That's not what happens, right? The other thing is classical cosmology says that light travels at the speed of light, and that's it, right? Well, a quantum physicist says, well, no, it goes a bit faster, it goes a bit slower on the small scale. So what actually happens in a black hole, there's stuff that actually time goes backwards. So instead of entropy increasing, entropy is actually decreasing, but only to an observer from the outside of a black hole. If you're an observer inside the black hole, you will actually see time going backwards, which is forwards to you, and entropy will be increasing. There's all sorts of mind games that you can play. You can't really look inside a black hole, so it's kind of hard to feel they agree, but now they don't agree.
Great.
It's good. Thank you.
That should be it. Okay. And I guess you.
Hi everyone, welcome to What's Up in the Sky for July 15th, 2023. Be sure to check out our gift shop in person or online. And you may notice that the gift shop online is a little bit low in product right now, but we're getting that replenished. And we're grateful for your memberships and donations as well, which help keep our educational programs running. Make sure you stop by and say hi during the summer daytime sessions. We'll be doing dome tours and planetarium shows throughout the day. And our summertime daytime hours are July 4th through September 29th, Tuesday through Saturday from 10 a.m. to 3 p.m. And there is an admission price because we do need to pay our staff and raise money for our educational programs. And so for seniors at age 65 and over, it's $12. Adults age 18 to 64, it's $15. Students age 18 to 25 with valid student ID is $8. Youth age 7 to 17 is $8. Children 6 and under is $0. And for the Masonic community on whose territory the observatory sits, it's also $0. So let's talk a little bit about sunset and sunrise times and a few other related things. Sunset is currently at 9:10 p.m., now 7 minutes earlier than the latest sunset on the solstice, with the sun setting at 305 degrees in the northwest. Sunrise is at 5:27 a.m., 16 minutes later than the earliest sunrise, with the sun rising 55 degrees in the northeast. And you might notice that the sunrise time is changing faster than the sunset time, and this is due to something called the equation of time. The Earth does not move around the sun at the same speed all the time, as we are not in a circular orbit. And it's also due to the fact that the Earth's axis is pointing in a fixed direction in space, so it actually shifts with respect to the sun. As a result, the time for solar noon shifts throughout the year. And I'm going to put up a little diagram here that helps illustrate that, and this is from Time and Date. It's an excellent website to explore about these things. And the midpoint is, as you can see right here, is when it's high noon is right at noon. on the clock is actually on June 14th. So is that actually true for Victoria, for example? So the midday point is, as I said, is drifting at the moment. On June 14th, it was actually at 1:13 p.m. in Victoria and is now at 1:19 p.m. So let's explore why that is, why it's not exactly at 1 o'clock. And of course, it's not at 12 noon because we're using daylight saving time. So also, it'll continue to drift, as you can see on this curve, until about July 25th, when it'll be 1:20 p.m. and reverse course and get earlier. So let's talk a little bit about why there's this little bit of an offset. And we actually have to take into account our position in the time zone. So because the Earth is spinning and the time zone is broad, high noon doesn't actually occur at the same time in every place in the time zone. In Nelson, BC, that actually occurs at 12:49 p.m. on June 14th. And so what city in BC is right at the midpoint of the time zone near the southern border, such that it's right at 1 o'clock on June 14th? And it turns out that Headley, BC is one such city, and that's a fairly small town some of you may not have heard of, but it's Headley, BC, a little bit to the southwest of Penticton. And so that's right at 1 p.m. And we're far enough west of that point here in Victoria that it takes another 13 minutes of the Earth spinning for the sun to reach high noon. By high noon, I mean right on the meridian, that north-south line that goes right through the overhead point. So in looking at these times, what about Cranbrook? And it appears to have a solar noon at 1:44 p.m. on June 14th. And you might think, well, that's going in the opposite direction. But if you check, you'll actually notice that Cranbrook is in the same time zone as Alberta. So in fact, if we were to put it in Pacific time, it would be at 12:44 p.m. So it fits with this idea of the sun moving from across the sky, causing the local noon to shift. So what about astronomical twilight right now? And it doesn't end until 12:03 a.m. and begins again at 2:35 a.m. So that gives us now more than 2.5 hours of full darkness. So we're starting to get a lot more darkness now in the night. And where is the moon? The moon is a waning crescent and is only 3% illuminated, and there'll be a new moon on July 17th, just a couple of days from now. And first quarter moon will be on July 24th. So we're now well into the darkest period of this month for looking for fainter objects in the nighttime sky. So I'm going to stop sharing this diagram right at the moment, and I'm going to share a view of the nighttime sky in Stellarium. And let me just shift the time a little bit here. And we're going to shift it such that it's just around 9:38 tonight here in Victoria. Okay. And we're looking over towards the west, as you can see. So Venus is the planet to watch at the moment. It just reached its brightest earlier this week. And you might actually start looking at it to see when's the latest in the month that you can see it. And so it might not be visible in about a week or so because it's actually overtaking the Earth and moving closer to, in angular terms, to the sun in the sky. And so it's now a thin crescent in a small telescope. And so how close is it to being between between us and the sun? And if you're to use what's called heliocentric coordinates, so that means coordinates centered on the sun, the angle between Venus and the Earth is now only 18 degrees, and it's decreasing. So currently Venus is at its best right around the time shown here, but around 9:30 at night. So how fast is it overtaking the Earth as well? And I think I mentioned this before, but it's only 5 kilometers per second faster. So it's moving at 35 kilometers a second, and the Earth is moving at 30 kilometers a second. And you'll notice here that Mars is faintly visible to the upper left of Venus, and really you have to wait until it gets a little bit after this time in order to see it properly. And I'm not sure I can actually shift the time here. Let's see if we can do that. So it has to get a little bit darker, and then you can see faint Venus, or pardon me, faint Mars to the upper left of Venus. So what about the morning sky? So let's actually see if we can shift over to that. And I'm going to just change the hour here. So it's about 3 in the morning. And we've got a whole bunch of meteor showers showing, but none of them are very spectacular. So we're going to get them out of the way. And there you can see Saturn and Jupiter up in the sky. And so Saturn rises in the east, rising at 1 a.m. And Saturn actually gets up a little bit earlier into our sky at about 11 p.m. And so, as you can see, Saturn is in sort of the south-southeast to the south at around 3:30 a.m. So it's going to be prominent in the evening skies in August. So that's something to look forward to as Saturn is returning to our skies. And I know that there's kids out there, such as my great niece, who have been waiting to see Saturn all year in the evening sky. And so it's finally coming out very, very soon. So onwards to talking a little bit about solar, solar activity. As we're nearing the solar max, there's lots of things happening. And there's another large sunspot visible all week. And as we noted last week, there are more on the way. And there's two ways that we can determine that more sunspots are coming. One method is called helioseismology, and it's a technique that uses the vibration patterns on the sun's surface to infer that a sunspot is present on the opposite side of the sun. And so basically the idea is kind of like having something poking into a pan of water and sending a wave across it. You'll actually get diffraction patterns around that. And so the sunspot on the opposite side will also affect the vibration patterns on the solar surface as the vibration patterns come around into view where we can see them. And another method, which I mentioned last week, is to use an actual camera at a different vantage point in the solar system. And the Perseverance rover on Mars, as I mentioned last week, has a camera with a solar filter on it, and astronomers use this to detect large sunspots on the sun that are not currently visible on the Earth. And in fact, they've confirmed that some of the sunspots detected with helioseismology are visible by using this method. So what is the current angle between Mars and the Earth? So earlier I talked about using heliocentric coordinates. So we use the angle between Mars and the Earth to find out sort of how far it is away and what its vantage point is on the sun. And so currently the difference in angle, remember I said Venus was 18 degrees separation in angle. With Mars, it's actually 117 degrees, so more than a right angle. So you could say that Mars is actually looking at the side of the sun, if you want to think of it in those terms, and it can see a whole different quadrant of the sun than we can see. So in order to observe these sunspots safely, remember, never look directly at the sun unless you have a certified solar filter. And the other way to do it is the best way, I think, and I think maybe the most fun, is to use a solar projection system with tinfoils. So lightly poke a very small hole, maybe with a pin or especially like a push pin, into tinfoil, and then stand with your back to the sun. So the sun would be behind me, and then hold up the tinfoil and project the sun onto a white piece of paper or a white card, and see if you can detect one of these new giant sunspots. And of course, if you look directly at the sun, even through a pinhole, you risk permanent blindness. So please don't do that. And as for aurora, you may have recalled that there was a display that hit the news this week that was potentially visible on Thursday, and that didn't happen as the blob of material that was ejected from the sun missed the Earth's magnetic field. And the fact that we can't predict these events that well reflects that we just don't have good enough monitoring systems for making these predictions. And you might ask, well, why should that matter, really, aside from the convenience of being able to predict an aurora? And certainly being able to predict whether these events are going to happen is very important, because so much of our communications and energy structure, and especially satellites, can be damaged by big solar storms. And so the best place to monitor what is happening with geomagnetic storms and aurora is to go to spaceweather.com and have a look at that site. And I'll see if I can actually just put that up here quickly and share it with everybody. And this is what I visit almost daily to see what's going on. And visiting daily is actually not a bad idea, because things do change quite quickly. And so you have to go back day to day to get it. In this view, there is an eruption from a sunspot, a dark eruption where there's material ejected and material spewed out in silhouette against the sun. And you can also see this view showing some of the giant sunspots that are currently visible. So this site also has a text monitoring system where you can actually just sign up for a text to your phone for a fee, and you'll be alerted when there's an aurora that's going to happen in your area. So that's about it for now. So again, thanks for supporting the Center of the Universe. Your donations are especially critical right now because we've been struggling to get grants, and we appreciate your moral support. And so please, in these tough times, keep looking up. Thanks a lot, everybody.